In the early days of electric power generation, the first customers were residential users who wanted electricity for lighting, its first real function. It was relatively easy to provide electric power in those days because the demand for power was predictable and consistent. Billing was also simple. Customers were charged by the number of light bulbs in the home. As new uses were found for electricity, appliances were developed for the home, and more services were installed to factories, where electric motors were replacing other power sources to drive machines and tools. Demand became less predictable and more irregular, and billing by the bulb became obsolete. Power utilities developed meters to keep track of how much power individual customers used and to keep track of their demand requirements. One kind of meter, designed for customers with unique demand requirements, is the demand meter. A demand meter is a meter that measures the average power that a customer uses during specific time intervals. In this program, we're going to look at demand metering concepts. Different customers have different demands for power. For example, one customer may need a little power over a long period of time, while another customer may need a lot of power in a very short period of time. These different demands affect the utility and what it costs the utility to provide electricity as it's needed. In this part of the program, we're going to look at why it became necessary for utilities to meter some customers' demand. We'll also look at how demand is defined by the power industry, and we'll identify several common types of demand registers. We'll start by looking at why it's necessary to meter demand. Power utility customers are billed based on what it costs to supply electricity to the customer. The cost of supplying electricity to a customer can be separated into two broad categories. One of these categories is the cost of energy, that is, the coal, oil, gas, or other fuel that is used to produce electricity. The other category is the cost of equipment, such as the generators, transmission lines, substations, transformers, and other equipment needed to deliver electricity to the customer. The cost to serve each of two customers may be different, even if both customers use the same amount of electricity. For example, customer A is a small manufacturer of parts. They use relatively small machines that are run by small motors. Their machines draw 10 kilowatts and run for 10 hours a day, so total energy use is 100 kilowatt hours a day. Customer B, on the other hand, is a specialty company making large custom-ordered parts. The big machine used on the custom pieces takes time to set up. When it's running, the machine uses 100 kilowatts, and typically it runs for only 1 hour a day. So total energy use by customer B is also 100 kilowatt hours a day. But customer B places a greater demand on the utility during the time it's drawing power, 100 kilowatts as opposed to 10 kilowatts. Also, the cost to the utility for providing service to customer B is greater than the cost for servicing customer A. That's because the equipment needed to provide service to customer B has to be higher capacity equipment. That is, larger and more expensive, from the generator all the way down to the distribution transformer and customer service wires. In order to fairly cover the cost of serving customers with vastly different demand requirements, the concept of demand metering was introduced. For electricity metering, demand is the average power used over a specified time interval. The meaning of demand can be explained more clearly using a chart showing power usage over a period of time. The vertical axis on this chart represents power in kilowatts. The horizontal axis represents time. The shaded area represents the amount of power that a given customer used over time. With demand metering, time is divided into regular intervals. The intervals may be any selected period, but they're usually 15, 30, or 60 minutes. What the typical demand meter measures is the average power required for each time interval. For example, these lines represent the average power required in each of the 4 time intervals shown. The demand value that the meter preserves or indicates is the maximum average power used in an interval during the billing period. So, for example, if this 3rd interval represents the maximum demand for a billing period, this average power is the value that the demand meter would indicate. And it's this value that would be used to help determine the customer's billing for the period. So, the concept of demand metering came about because the unique power demand of some customers required a method of billing them for their fair share of the higher cost of providing service to them. Demand metering is based on the concept of measuring the average power used over a specified time interval, and demand billing is based on the maximum demand for a billing period. We'll look at how demand meters get demand readings later in this program. But for now, let's identify 3 common types of demand registers. Each type is related to the kind of mechanism used to measure demand. One type of demand register is the mechanical demand register. It uses a motor and gear mechanisms to measure demand over specified time intervals. A second type of demand register is the thermal demand register, which uses small transformers, heater elements, and bimetallic coils. The third type of demand register is the electronic demand register, which uses an electronic microprocessor. Each of these demand registers is associated with a particular method of responding to and indicating demand. Now, when I say method, I mean the principle of how the register responds to and indicates demand, not the mechanics. We'll look at demand metering methods in the next part of this program, and we'll look at the mechanics of demand register operation later. Before continuing, review the material in your text on the demand concept and answer the questions provided. Demand can be measured in kilovolt amperes, kilovars, amperes, or any other suitable electrical measure. But probably the most common demand measurement for billing is the kilowatt demand. Now, a kilowatt demand meter is typically a kilowatt-hour meter with a demand register added to it. The demand register can be mechanical, thermal, or electronic. Each of these 3 types of demand registers is associated with a method of responding to and measuring demand. The mechanical register is associated with what is known as the block interval method. The thermal register is associated with what is known as the lagged method. And the electronic register can be programmed for either method. In this part of the program, we're going to look at the block interval and lag methods of demand metering. The first method we're going to look at is called the block interval method of metering demand. This method is related to the response of mechanical demand registers and to electronic registers that have been programmed for a block interval response. To keep our discussion simple, we'll look at the block interval method as it relates to a mechanical register. The mechanical demand register has an indicator of some kind, such as this sweep pointer. At the beginning of a billing period, the pointer is set at 0. The register also has a pusher arm. The pusher arm is linked to the disc of the meter through a gearing mechanism. The pusher arm is moved upscale in proportion to the rotation of the disc. As power is used, the pusher arm pushes the pointer upscale at a rate or speed that's proportional to the amount of power being used. For example, if a lot of power is being used, the pusher moves the pointer relatively fast. If only a little power is being used, the pusher moves the pointer more slowly. The mechanical demand register also has a timing motor to measure the demand interval and cause the pusher arm to reset to 0 at the end of each interval. The principle of how a mechanical demand register responds to and measures demand is called the block interval method. A simplified chart will help us see how this method works. The vertical axis of the chart shows kilowatt load and is marked off in increments of 5 kilowatts. The horizontal axis shows time and is marked off in 15-minute demand intervals. Here's an example of how the pusher arm and pointer responded during 3 consecutive demand intervals. The dotted line represents the kilowatt load. The dashed line represents the movement of the pusher arm. And the solid line represents the movement of the pointer. As shown on the chart, the load was a steady 5 kilowatts during the first 15-minute interval. In response to the load, the pusher arm of the demand register steadily moved the pointer upscale at a rate proportional to the load, so that by the end of the interval, the pusher arm and pointer indicate 5 kilowatts. This is the maximum demand, or average power used, during the first interval. At the end of the interval, the pusher arm reset back to 0 so that it could begin measuring the average power used for the next interval. The pointer remained at the 5 kilowatt indication to provide an indication of the maximum demand up to that point in time. For the second 15-minute interval, the load increased to a steady 10 kilowatts. The pusher arm advanced upscale at a faster rate than it did in the first interval, in proportion to the new load. The pointer remained at 5 kilowatts until the pusher contacted it and moved it upscale to 10 kilowatts by the end of the second interval. At the end of the second interval, the pusher arm again reset to 0, while the pointer remained at its maximum indicated demand. For the third interval, the load stayed at 10 kilowatts for about 5 minutes. Then the load dropped back down to 5 kilowatts. The pusher arm advanced at a 10 kilowatt rate for the first 5 minutes of the interval. Then the pusher slowed down to a 5 kilowatt rate in proportion to the load for the last 10 minutes of the interval. By the end of the third interval, the pusher had advanced to about 6.66 kilowatts before resetting. 6.66 kilowatts is the maximum demand, or average power used, during the third interval, which is more than 5 kilowatts but less than 10. Since the demand during the third interval never reached the maximum demand for the second interval, the pusher did not advance far enough to move the pointer. So the maximum demand indicated on the demand register remains at 10 kilowatts. So the block interval method of metering demand is associated with a mechanical or an electronic demand register. With this method, demand is registered in blocks of regular timed intervals. The demand indicated at the end of an interval represents the average power used during the interval, and only the maximum demand indication is retained by the meter during a billing period. Another method of metering demand is the lagged method. This method is related to the response of thermal demand registers and to electronic registers that have been programmed for a lagged response. Like the mechanical demand register that we just looked at, the thermal demand register also has a pointer and a pusher arm. However, in a thermal demand register, the pusher arm is linked to temperature-sensitive bimetal coils. The coils are surrounded by heater elements, which heat the coils in proportion to the load being measured. The coils expand and contract to move the pusher arm up and down the scale. The principle of how a thermal demand register responds to and measures demand is called the lagged method. This simplified chart will help us see why the response of a thermal register is referred to as the lagged method and how the lagged method works. On this chart, the vertical axis shows percentages of kilowatt load. The horizontal axis shows time and is marked off in 15-minute increments. The dotted line represents the kilowatt load. The dashed line represents the movement of the pusher arm. And the solid line represents the movement of the pointer. The curve of the pusher arm and pointer is a typical representation of the temperature changes that occur when a substance is exposed to a steady heat source. In a thermal demand register, The heat source is the heater elements, and the substances being heated are the bimetal coils. The coils respond to the heat by moving the pusher arm upscale. The reason for referring to a thermal demand response as a lagged method can be explained using the curve that represents the motion of the pusher arm and pointer. Notice that the thermal response to a steady load is fairly quick at first. By industry definition, a thermal demand register indicates 90% of a fixed load in 15 minutes. The demand interval for a thermal demand register is defined as the time needed for the temperature sensing elements to achieve 90% of full response when a steady load is applied. So a typical demand interval for a thermal meter is 15 minutes. And in 15 minutes, the thermal response is only 90% of the load. Notice that the thermal response doesn't near 100% of the load for quite some time after the 15-minute interval. This is where the term lagged comes from when referring to the response method of thermal registers. It's also important to note that demand registration for a thermal meter is continuous. Notice by the dashed line indicating the movement of the pusher arm that the pusher arm does not reset at the end of regular time intervals. Instead, it moves up or down scale in response to temperature changes resulting from load changes. For example, here the load decreased and the pusher arm moved down scale. Notice also, as indicated by the solid line, that the pointer remained at the maximum demand indicated before the load dropped. As with the mechanical demand register, the pointer will only be moved upscale if the demand increases beyond its previous maximum demand. So, with the block interval method, demand is registered in specific blocks of time, while with the lagged method, demand is registered continuously. With both methods, the demand indication on the meter represents the maximum demand during a billing period, which is the same as the maximum average power used. Now, in this part of the program, we looked at the principles of the block interval and lagged methods of metering demand. The mechanics of how demand is metered vary, depending on whether the demand register is mechanical, thermal, or electronic, and depending on other design and functional variations. Throughout the rest of this program, we'll look at the components of mechanical and electronic demand registers. We'll begin with mechanical registers, but before continuing, review demand metering methods in your text and answer the questions that follow. In the next two parts of this program, we're going to look at various kinds of mechanical demand registers. We'll also look at their main components and the function of those components. Two common types of mechanical demand registers are the indicating register and the cumulative register. Let's look at the indicating register first. An indicating register is a type of register that indicates only the maximum demand for each billing period. There are two basic models of indicating registers. These are the sweep pointer indicating register and the dial indicating register. The sweep pointer indicating register has a single pointer and a graduated arc-shaped scale. Each increment on the scale represents a given value. The value represented can vary depending on the full-scale value of the register. The accuracy of a sweep pointer is designed to be plus or minus 1% of full scale. In other words, if the demand value typically registers near the high end of the scale, the reading is accurate to within 1%. However, the readings farther down the scale may be less accurate. For example, full scale for this register is about 70 kilowatts. 1% of full scale then would be 700 watts. So this register is designed to be accurate to about plus or minus 700 watts. Mid-scale for this register is about 35 kilowatts. An error of 700 watts here is 2% of 35 kilowatts. So a reading at mid-scale would be accurate to plus or minus 2%. For a reading at 1/4 scale, an error of 700 watts would result in an accuracy to only plus or minus 4%. Readings are less accurate downscale on a sweep pointer register. Because of this, a sweep pointer register needs to be matched to the meter's full overload capability, so that demand typically indicates above mid-scale, while still allowing capacity for the pointer to indicate overload demand without pegging. Three register classes that are commonly used are the Class 1 register, which has a full-scale capacity of 166 2/3% of the meter's full load rating, the Class 2 register, which has a capacity of 333 1/3% of the meter rating, and the Class 6 register, which has a capacity of 666 2/3% of the meter rating. Some registers are designed to have a dual range capacity. For example, this dual range register is designed for use in a primary metering application. It has a full-scale capacity of about 70 kilowatts. By reversing the scale and shifting a gear, the full-scale capacity could be doubled to about 140 kilowatts. Regardless of the register class or range, sweep pointer registers are driven by the rotation of the meter's disk shaft. When the disk shaft rotates, it drives a gear train. Part of the gear train turns the dials that indicate kilowatt-hour use. A separate part of the gear train causes the pusher arm of the demand register to push the demand pointer upscale. While this is taking place, a timing motor is turning a timing gear train. Demand meters typically have a time interval indicator, like this one, to indicate about how much time has elapsed at any point during an interval. At the end of the block interval, the timing gear train causes or allows the pusher arm to reset to 0 so that it can begin registering demand for a new interval. After the demand for a given billing period has been read and recorded, the demand pointer is manually returned to 0. The demand register is now set to indicate demand for the next billing period. So, a sweep pointer indicating demand register has a single pointer and a graduated arc-shaped scale, and is designed to be accurate to within plus or minus 1% of full scale. There are three classes of sweep pointer registers that are commonly used, and the main components of a sweep pointer register are the register gear train, the pusher arm, the sweep pointer, and the timing motor and its gear train. The other indicating register that we identified earlier is the dial register. We'll look at the dial register as well as the cumulative register in the next part of this program. Be sure to review the material in your text on the sweep pointer register before continuing. Earlier in this program, I said that there were two types of mechanical demand registers, the indicating register and the cumulative register. In the last part of this program, we looked at one indicating register, which was the sweep pointer demand register. In this part of the program, we're going to look at a second indicating register, which is the dial register. We'll also look at the mechanical cumulative demand register. The dial register typically uses three dials to indicate maximum demand: a hundredths dial, a tenths dial, and a units dial. A decimal is placed between the dials as needed for full scale. With three dials, the demand reading is more precise than with a sweep pointer register. The accuracy of a dial register is designed to be plus or minus 1% of reading, as opposed to the 1% of full scale for a sweep pointer register. This means that a dial register should be accurate to plus or minus 1% for any demand that it indicates. For this reason, dial registers don't need to be as closely matched to the meter's full overload capability. The operation of a dial register is similar in principle to the operation of the sweep pointer register, but it's more complex in its gearing. The gear train drives three pointers rather than just one. The pusher arm is an internal mechanism, and it resets at the end of each interval, just as the pusher arm for the sweep pointer register. The demand dials are moved upscale only when the demand exceeds the demand for previous intervals during a billing period. When they are not moving, the dials indicate the maximum demand attained during the billing period. If demand exceeds the rating of the register, the overload is indicated when the high demand dial enters a black sector. This tells the meter reader the same thing that a peg sweep pointer would, that demand has exceeded the capability of the register. To return the demand dials to zero at the end of a billing period, the reset lever is rotated until the 3 dials indicate zero. Then the reset lever is rotated back to its normal or neutral position. So a dial indicating demand register has 3 dials and is designed to be accurate to plus or minus 1% of the reading. It has operating mechanisms similar to those of the sweep pointer register, but with a more complex gear train. And register overload is indicated when the high demand dial enters a black sector. So now we've looked at 2 indicating demand registers, the sweep pointer register and the dial register. Both are mechanical demand registers with similar components, and both operate on the block interval principle of registering demand. The other mechanical demand register that we should look at is the cumulative demand register. A cumulative demand register is a type of register that indicates maximum demand for each billing period, as well as the sum of the maximum demands from previous billing periods. This dial indicates the maximum demand for a billing period. It's often called a test dial, and it's similar to a sweep pointer. However, this indication is not read as the maximum billing demand. Instead, it's primarily used during testing to verify proper register operation. These 4 dials indicate the sum of the maximum demands from previous billing periods. They're similar to the 3 dials on a dial register. However, here, they indicate the cumulative demand over numerous billing periods. This is how the cumulative demand dials work. When the cumulative demand register is first put into service, all the demand dials start at 0. The test dial moves upscale to indicate the maximum demand over the block intervals for a billing period. When the demand is read at the end of the billing period, the reading on the test dial is transferred to the demand dials. The demand is transferred through the register gear train by pushing a reset button. When the reset button is pushed, not only is demand transferred to the demand dials, but the test dial is also reset to 0 so that it can begin indicating maximum demand for the next billing period. When the demand is read at the end of a billing period, the positions of the demand dials are noted. They should be in the same positions that they were left in at the beginning of the billing period. Then the reset button is pressed to transfer the demand for the current billing period from the test dial to the demand dials. This operation also resets the test dial to 0. After the demand is transferred, the demand dials indicate the new accumulated demand reading. To determine the demand for the current billing period, the previous demand indication is subtracted from this new accumulated reading. Now, in the last 2 parts of this program, we looked at 3 types of mechanical demand registers. These were the sweep pointer and dial indicating demand registers and the cumulative demand register. Each type is operated by the rotation of the meter disc shaft through a gear train. Each type uses a timing motor to provide the interval timing. Each type operates on the block interval principle of registering demand. Another kind of demand register that may be used is the thermal demand register, which operates on the lagged principle of registering demand. Because of its limited use, we won't look at the thermal demand register, but instead, in the next part of this program, we'll look at the electronic demand register, which is rapidly replacing both mechanical and thermal registers. Remember to review the material in your text on mechanical demand registers and answer the questions provided before moving on. The electronic demand register is a relative newcomer to demand metering. It was made possible by the development of non-volatile electronic memory systems. A non-volatile memory system is able to store data even during a power outage without requiring battery backup. Many different kinds of electronic demand meters are becoming available. In this part of the program, we're going to look at examples of electronic demand registers that work as part of electromechanical meters. The heart of an electronic demand register is a microprocessor, which is an integrated circuit that's responsible for the actions of the register. The microprocessor is operated by electronic pulses. The pulses can be created a number of different ways. For example, this meter uses a photo-optic assembly. One part of the assembly contains a light-emitting diode. The other contains a photocell that senses the light. The two parts of the photo-optic assembly fit above and below a vane, or shutter, that is mounted on the meter's disk shaft. As the shutter rotates with the meter disk shaft, the shutter intermittently interrupts the light path between the diode and the photocell. This generates pulses that are counted and stored by the microprocessor. The faster the meter disk and shutter turn, the more pulses are generated, counted, and stored during the demand interval. Here's another electronic demand meter. It also uses a photo-optic assembly that includes a light-emitting diode and a photocell. The photo-optic assembly is mounted under the meter disk, which has a printed pattern on it. The diode beams light onto the disk. When the light hits a shiny part of the disk, it's reflected back to the photocell. When the light hits the dark printed pattern on the disk, it does not reflect back to the photocell. As the disk rotates, it alternately reflects and interrupts the light path to the photocell. This generates the pulses that are counted and stored by the microprocessor. The faster the disk turns, the more pulses are generated, counted, and stored during the demand interval. The information that an electronic demand register can record, track, or display varies with the manufacturer, model, and how the register is programmed. Typically, electronic demand registers are accurate to within a few pulses. A pulse doesn't even equal one disk revolution, so accuracy is measured in tenths of a % of reading. Many features of the electronic demand register are programmable. For example, the register can be programmed to any time interval desired. The register can also be programmed to provide what is known as a rolling demand interval. With a rolling interval, the microprocessor looks for the block of time with the maximum demand. That block of time may include demand that would normally be registered in successive time intervals. For example, here, the demand for a typical fixed 15-minute time interval is 6 kilowatts. The demand for the next fixed 15-minute interval is 8 kilowatts. If a rolling demand interval is used, the block defined from 10 minutes in interval 1 to 25 minutes in interval 2 shows a demand of 11 kilowatts. Rolling demand overcomes the user's ability to split large loads between two intervals and effectively lower the indicated demand. Another programmable feature of many electronic demand registers is the mode of operation. For example, the mode may be programmed for indicating demand, or cumulative demand, or both indicating and cumulative demand. Electronic demand registers can be programmed to process and display so many different kinds of information that most now have 3 modes of operation. These are the normal mode, the alternate mode, and the test mode. Utilities typically limit the normal mode display to information that a meter reader would typically need, such as kilowatt hours and kilowatt demand. The alternate mode is available to display other information useful to field technicians and shop personnel, such as time remaining in an interval, kilowatt demand overload, cumulative kilowatt demand, number of power outages, and so on. The test mode displays information needed to check the proper operation of the register, such as a pulse count to check that the pulses are being properly received by the register, time left in an interval to check internal clock operation, and segment check to make sure that each segment in the liquid crystal display is functioning. The features and flexibility of electronic demand registers vary with manufacturers. Most can be programmed by the user to customize the meter to the user's needs. Now, in this program, we looked at the concept of demand. why it's needed. We also looked at the block interval and lag methods of metering demand. And we looked at the components and the function of the components in various mechanical, thermal, and electronic demand registers. The actual demand registers that we looked at are just a small sampling of the many different makes currently in use. But the principles of operation and the common components and functions that we looked at provide a foundation that will help you no matter what type of demand meter you work with.